Up into this video, we've been spending a lot of time learning about sine of x. We've been spending a lot of time learning about cosine of x. And the thing is, these graphs here are very useful for us to model nature. And what I mean by model nature is that often in maths we would learn about a certain topic. Let's say sine of x. We would learn we would learn so that we know everything there is to know about this topic here. So for example, we know how to squeeze everything inwards. We know how to stretch everything up or down. We know how to change a period of this thing. We know how to change the amplitude. We know this thing inside out. Often in maths we would learn something. We would learn a certain topic and we know it inside out. Once we know it inside out, we would look to nature and then map nature onto what we know, what we're really good at, which is sine. We are now sine experts, if you like. We could map nature onto our graph. And once we've mapped nature onto a graph, we can make calculations. So for example, if this is a graph of, let's say, temperature and time in hours, okay? Let's say, well, once we've mapped, most of the time we don't understand nature, so we would map nature onto what we know. In this case, we will map it onto our sine of x graph, and then once we've mapped nature onto our graph, we can work out, let's say, the temperature at when the time is 40 hours, or well, yeah, we would work out this point, because this point here, when time is 40, this point here represents our temperature. Or we could extrapolate. We could go into the future and we could predict the temperature when the time is 4,444 hours. We can predict into the future, or we can go into the past. We can make predictions, basically. So for example, if you look at this here, if you look at the body temperature of a human being, if you draw a graph of temperature and this here is time. Let's say time is in hours, okay? So you've got 24 hours here. Now, our body temperature is roughly 37 degrees. So if you were to draw a graph, it would look something like this. Roughly speaking, it would look something like this, 37 degrees. So when an environment is cold, let's say 10 degrees, okay, we would try and keep our body temperature at 37. So we would turn on the heater, or we would wrap our body around a blanket. So if this is 10 degrees here, we would do everything in our power to keep our body temperature at 37. So when it's cold, when the environment is cold, we can either turn on the we can turn on the heating, or we can wrap ourselves up in a blanket. So when you wrap yourself up in a blanket here, your body heats up the air around here. So the air around here would be near 37, whereas the air around here would be 10 degrees Celsius. So the blanket creates some sort of barrier between our environment and the air near our body. My point is that we would always try and keep our body temperature at 37. If it drops, I don't know, to 35, then you're in trouble. Okay, if it goes beyond, if it's, I don't know, 40 degrees, then you're in trouble, basically. Our body, we would always try and keep our body temperature at 37. Now, if you look at a cold-blooded animal, let's say a lizard, okay, if you look at a lizard, the body temperature of the lizard, it changes with the environment. So if it's hot, if it's hot here, the body temperature of a lizard will increase with the environment. If it's cold, it will decrease. If it's hot, it will increase. So roughly speaking, now I'm not saying it will look like this in real life, but I'm saying we could use a sine graph to model the body temperature of this lizard. You see, when it's cold here, the lizard doesn't really care. Its body temperature will match the environment. So at around, but the downside of that is that when it's cold, the lizard cannot move around. It's it, it, it can only move around when it's at a certain, when it's, let's say when it's in a certain range here. Let's say when it's in this range here. Hang on. When it's in this range here. Hang on. Let's say the lizard can move around when its body temperature is within this range here. When it's at night, it needs to go into hiding because it cannot move around. It cannot move around when its body temperature is below a certain level. It saves energy. You see, with us, our body temperature is always at 37. So we can, you see, we can always move around, even when it's cold, when it's 10 degrees. We can always move around, even when it's hot. Let's say 40 degrees. Well, let's say 50 degrees. We could turn on the air conditioning, or we could turn on the fan to keep our body at 37. But the point is, when it's at 50 degrees, we can still move around. We can still run away from predators. We can still fight. We can still move around. But with a lizard, it cannot move around when it's too. Hang on. With a lizard, when it's cold, it cannot move around. When it's cold, it has to go into hiding. So, but the downside is that the downside of us keeping our body temperature at 37 is that we need to constantly eat. We need to eat quite a lot of food in order to keep our body temperature at this level here. We use a lot of energy in order to keep our body temperature constant. If you look at a lizard, when it's cold, it doesn't move, so it saves a lot of energy. So the good side about this system is that you don't need to eat as much. You don't need to hunt to go out and eat as much. We human beings, we are keeping our temperature at this constant level here. But the downside is that we need to eat a lot. The lizard here, the downside of the lizard is that it cannot move around at certain temperature. But the thing is, it doesn't need to hunt as much food. It doesn't need to eat as much food. In the next video, I will give you some more examples of why it's useful for us to use sine graphs and cosine graphs. Okay.